As humans, we're well aware we need water to live. Fortunately for us, we live on a water planet. But that doesn't mean we have an entire globe of H2O to use as we please. So just how does the usable water break down for us? A giant 97% of Earth's water is in the ocean, so we can't use that. 3% is fresh water, but even in that small sliver, about 2% is locked in glaciers, ice caps, and groundwater. That leaves about 1% of the fresh water on Earth that is accessible and usable by humans.
Water is the fundamental ingredient for life on Earth. Looking at our Earth from space, with its vast and deep ocean, it appears as though there is an abundance of water for our use. However, only a small portion of Earth's water is accessible for our needs. How much fresh water exists and where it is stored affects us all. Nearly 2/3 of this fresh water is stored in the polar ice caps, snowpacks, and glaciers, making it inaccessible for long periods of time. The water cycle is dynamic. It describes the continuous movement of water on, above, and below the surface of the Earth, and the transitions from one state to another. Sea surface temperature, surface winds, and air temperature influence the rate of evaporation at the ocean surface. In the tropics, warm ocean surface temperatures support high rates of evaporation. Wind also increases evaporation. When the air's temperature is warmer, it can hold more water. While the atmosphere does not store a large quantity of water compared to the ocean, rivers, and lakes, it can transport water quickly from one place to another. Low-lying regions of the atmosphere with high moisture and strong winds can form atmospheric rivers to transport water horizontally. Clouds are formed as water vapor cools and condenses into droplets and ice crystals. Clouds and water vapor act as insulators in the atmosphere. Clouds help shield the Earth from the sun and trap heat from below. When cloud particles grow large enough, they may fall out as rain or snow. Under the right conditions, areas of precipitation can grow into large storms. As storms grow, they transfer heat vertically into the upper atmosphere. The migration of storms helps to distribute heat between the equator and poles, shaping wind patterns globally. How storms grow and intensify depends on atmospheric moisture, surface temperatures, and wind patterns. Precipitation is concentrated in some parts of the world and scarce in others. It can vary substantially from season to season and from year to year. Water that falls on the land surface as precipitation is stored within snowpacks, lakes, reservoirs, soils, and underground aquifers. Water availability varies from place to place and over time. The availability of water affects the type and abundance of vegetation, the primary source of food for animals and people. Extreme water cycle variability, unusually dry or wet conditions, impacts humans worldwide. Each year, hazards such as floods exact a costly economic and human toll. Most of the water that falls onto land remains stored there for weeks or more. Snowfall is stored as snowpack or ice. Meltwater and rainfall are stored in lakes and soils. Some of the water is absorbed by plant roots or drains into the water table. Eventually, the water will evaporate to the atmosphere or return to the ocean in streams and rivers, providing a source of nutrient-rich water that supports ocean life. Sensors on a suite of NASA satellites observe and measure water on land, in the ocean, and in the atmosphere. These measurements are important to understanding the availability and distribution of Earth's water, which is both vital to life and vulnerable to the impacts of climate change and a growing world population.
As humans, we're well aware we need water to live. Fortunately for us, we live on a water planet. But that doesn't mean we have an entire globe of H2O to use as we please. So just how does the usable water break down for us? A giant 97% of Earth's water is in the ocean, so we can't use that. 3% is fresh water, but even in that small sliver, about 2% is locked in glaciers, ice caps, and groundwater. That leaves about 1% of the fresh water on Earth that is accessible and usable by humans. Let's imagine all of that accessible fresh water fits into this tiny pool. Now we'll get to some small numbers when we look at global freshwater. There really is a small fraction of usable and accessible freshwater on this water planet, so how do we use that tiny pool? In the United States, about 49% is used in thermoelectric power production, while agricultural irrigation makes up about 31%. 11% goes to public use in our cities and towns, 4% goes into industry and manufacturing, and 1% is domestic use. The water coming out of our faucets largely comes from precipitation. Measuring how much or how little precipitation falls can impact how we live our daily lives. Elsewhere around the globe, in developing countries, agricultural irrigation accounts for about 70% of freshwater use, while industrial use is 20% and 10% for public consumption. In places where access to usable freshwater is greatly limited, knowing when and where precipitation may fall is critical to livelihoods. Precipitation replenishes these tiny reservoirs of fresh water, and data from the Global Precipitation Measurement Mission will help farmers, ranchers, and policymakers in these regions plan for periods of drought, flooding, and other extreme weather.
Water is all around us, and its importance to nearly every natural process on Earth cannot be underestimated. It is the only compound that can be found naturally as a liquid, gas, and solid. The process by which water moves around the Earth, from the oceans to the atmosphere to the land and back to the ocean, is called the water cycle. Water regulates climate, storing heat during the day and releasing it at night, and carries heat from the tropics to the poles by sea and by air. Let's follow a single molecule of water beginning in the ocean through the paths it might take before eventually winding up right where it started, back in the big blue sea. The fuel for this journey will be provided by our planet's prime energy source, the sun. During the day, the sun heats up the air and ocean surface, causing water molecules to evaporate. Evaporation occurs when a liquid molecule of water escapes into the air as a gas. This scientific visualization shows how water evaporation, indicated in turquoise, is driven by the energy of the sun. Notice how the rate of evaporation pulses over land. It speeds up in the day and almost disappears at night. Over the ocean, evaporation appears to remain constant both day and night. Water in the air in gas form is known as water vapor. The molecule is now fresh water, having left the ocean salt and other particles behind.
The water evaporates and goes into the atmosphere, and then it doesn't necessarily just turn around and fall as rain or snow.
Condensation is the process by which water vapor molecules cool, stick together, and become liquid again in cloud formation. This often happens high in the atmosphere, where the temperature is much lower than it is near the surface.
What happens in the atmosphere is, just like we have currents in the ocean, we have winds in the atmosphere that actually, to some extent, drive what goes on in the ocean currents. Materials in the atmosphere can travel actually a great distance, sometimes, a quarter of a way around the world, until they get to the point where they actually turn into rain or snow and thereby fall back to the ocean or fall back to the land.
This is called precipitation. If the water molecule falls on land as snow, it may be stored for a very long period of time in a polar ice sheet or mountain glacier, depending on climate conditions.
When rain falls or the snow melts, typically the next place it goes, it infiltrates into the soil. So soil is not a solid, it's not like a rock. There are pore spaces in there, and those can be filled with water. And typically there is a certain amount of water in the soil at all times. If the soil was completely dry, then plants wouldn't be able to grow.
If soil becomes saturated, any additional rainfall will collect in puddles and streams. Soil water that percolates deep enough will help to recharge an aquifer.
An aquifer is any underground geologic formation that stores water. So it's typically either a rock with a lot of cracks in it, or it's sandy layer. Sand has a lot of pore space in it, it can store a lot of water.
The water molecule might remain in an aquifer for more than 1 million years. More likely, it would help to replenish a stream, which would feed into lakes and rivers. Eventually, the water molecule will return to where it started, the ocean. People also have a role in the water cycle. By pumping water out of the ground for irrigation, cutting down forests for development, and building roads and other concrete surfaces that lead to runoff, people can have a serious impact on the path a water molecule takes.
The most obvious way that people affect the water cycle are the ways that we control the water after it's fallen on the land surface as rain or melts as snow. But we have put in dams and rivers to hold this water. We also pump the groundwater out and use that. So it's these water resources, we call them, are really us taking a natural part of the water cycle and using it to our benefit.
The water cycle also affects and is affected by climate variations.
The water cycle is one of the ways that we will really feel any changes in climate. So climate changes will feed back to water cycle changes, things like how much precipitation an area receives, the frequency of droughts and floods and this sort of thing.
The water cycle is the adventurous journey that water takes through the oceans, atmosphere, and land, driven by the sun. Improving our understanding of the water cycle and how it is changing will be critical for future decisions related to water management, agriculture, natural resources, and climate change.